In this video, I want to show you how to use Desmos to create a new calculated column in order for beginning physics students and other people who want to find linear relationships that fit nonlinear scatter plots. In this case, we have the diameters and the areas of some circles. This is all measurement data, so this scatter plot shows how real circle diameters and areas relate to each other. The unit's centimeters. But that doesn't really matter for our purposes. This looks a little bit linear, but not completely, and we can test that like we always do by just doing regression. So we'll add an expression, and that expression will have the vertical axis, which is A1, and then a tilde to prompt regression, and then M for slope, and then D1 is the horizontal axis, that's the diameters, plus B. And there are two things that give us strong indication that a line isn't a good pattern. One of them is the R-squared value isn't really good, 0.9871. And the even more disturbing one is that the vertical intercept is negative 36. That's too large to ignore. Also, it's meaningless because negative area doesn't mean anything, especially for a circle whose diameter should be 0, and so its area should also be 0. So this obviously is not the right pattern. The line isn't a good fit. And if you look at it, you can sort of see that there's an upward curving parabolic looking shape to it. If there were more points with smaller diameters, more circles with smaller diameters, I think it would be more obvious even yet that it's an upward swooping parabolic shape. So we're going to look for a different pattern, and of course what we do to linearize a parabola is square horizontal axis values, and that's not so easy to do in Desmos. It takes a little bit of a trick, but it's not too hard, and I'll show you how to do it. First thing I'm going to do is get rid of this regression and just take it off of the graph because it's not useful. The next thing I'm going to do is I'm actually going to add an expression, and this expression is going to be a set of data points. So how I do that is I'm going to put parentheses, and I'm going to plot not a point, but I'm going to plot a whole series of points. And that's going to be the square of the diameters. So I'm going to go D1 and then up caret 2, so I'm squaring it. And then I'm going to put a comma, and then I'm going to put A1. And then I'll close the parentheses. And now what it has just done is it's made a plot that has all of the diameters squared as a horizontal axis value, and the areas as a vertical axis value. What we see right now is the same graph that we had before. So I'm going to first off turn off the area points. And the other thing I'm going to do is I'm going to change the scale actually of the horizontal axis, because if I square the diameters, the smallest point will be around 16 because the smallest diameter is around 4, and the biggest one will be over 100. So I'm just going to go up to my little wrench icon, and on the x-axis scale, it was scaled at 15. I'm going to change that to 150 just to make sure everything fits, and there we can see our point. So right now, diameter squared is on the horizontal axis, and area is on the vertical axis. The next thing I'm going to do is I want to find regression and find out if a line is now a good fit for this linearized data. And I can't do that with this expression plotted on here right now. So I have to turn this into a table so I can do regression. How I'm going to do that is I go up to this little gear icon and I click on it. One of the options I get for this set of coordinate points is convert to table. If I click on that, a table appears, and it's just a table that has those data. So X was the diameter squared data. I'm just going to change that to be a little bit more meaningful by making it S, and I'm going to put S1 there so it recognizes it as a table. So S for squared. And then Y, I'm going to change that to area because that's what it is, but I already have A1 being used, so I'm going to change that to A2. Now that I have a table with my data in it, I can do regression analysis on that table. So I click on Add Item, Expression, and now I want to find out how area corresponds to the square of the diameters. So A1, A2, and then the tilde, M, S1, and remember that's the diameters squared, plus B. And what we can see is visually the line goes through a lot of the points. Looks like a pretty good fit. The r-squared value is very high, 0.9998. And the vertical intercept is small compared with the highest area value. It's less than 5%, so we can assume that it should be ignored. And that jives with the idea that a circle of 0 diameter should have no area. Another thing that's very interesting about this is the slope. The slope here is 0.763. The formula for area of a circle that everybody knows from middle school math classes is pi r squared, which would be pi times diameter over 2 squared, which would be pi times the diameter squared over 4. So the slope should be pi divided by 4. And if we double check that by just taking pi on a calculator and dividing by 4, that value is 0.785. And the slope we actually got was not far from that, 0.763, so within a few percent, and it's reasonable to think that we have the right relationship here. So that's how you can linearize data using Desmos. The steps are plot the original table values modified the way you want to as a set of coordinate pairs, convert that into a table, and then do regression analysis on the table and see what your fit is like. Hope this helps.